Hello everyone, and welcome to this introductory presentation for DYNAP-SE1 neuromorphic chip. Today I will be presenting the overview of what the chip is, what it's doing, and hopefully give the intuition of the experience of working with one of these chips without going too deep into details about the installation and the coding behind. But I will point out the resources where that information could be found. And as a quick illustration here, I have these flickering neurons which are currently active on one of the DYNAP-SE1 boards that I actually have in front of me right now, and we will return to them a bit later. But currently, I will show some slides to introduce the board. So DYNAP-SE1 is a mixed signal asynchronous analog digital neuromorphic processor developed at the NCS group of Institute of Neuroinformatics. These chips are packaged using these blue boxes. And each blue box, in fact, contains 4 individual DYNAP-SE1 chips with 4 cores each, with each core having 256 sleek integrate and fire neurons. All of those 4096 neurons in total are connected to the same asynchronous digital router. By programming this router, we can connect practically any neuron to any other one, creating either feed-forward or recurrent or any architecture of spiking neurons you can come up with, which makes DYNAP-SE1 rather a general-purpose neuromorphic processor rather than dedicated to solve a specific task. When creating a connection between the two neurons, the spike could be routed through one of the 4 synapses, one of the 2 excitatory ones implementing AMPA or NMDA mechanisms, or one of the 2 inhibitory ones, GABA A or GABA B, or subtractive or multiplicative inhibition. From all of the neurons of the chip, we can record spiking events or the action potentials from every neuron, but also it is possible to monitor the subthreshold dynamics of the neurons using the analog outputs that you can see over here. And you observe traces like this. So you see the spiking dynamics with the refractory period, positive feedback, and you can also observe synaptic behavior where you can tune the amplitude of the pulse as a weight and the time constants. And even though you can observe only one neuron at a time, pretty easily through software, you can switch between the neurons in real time and verify that all of them are working the way it is intended, as well as you can use that for calibration. Those were the features, but some of the constraints when working with DYNAP-SE1 chips, such that because of the area limitations, all of the 256 neurons of a single core share the parameters. So it means that when you're setting some parameter, namely the time constant or the synaptic weight, they have to be shared between the neurons of the entire core, which means that you are effectively setting the mean for some distribution of parameters. And all of the circuits of the chip are subject to variability or mismatch, which is caused by the sensitivity of the subthreshold circuits to silicon doping variations, which means that the imperfections in manufacturing the chips leads to heterogeneity of behavior of individual parameters of the circuits, and their overall behavior is up to 10 to 15%, which means that all of the architectures implemented on the chip has to have these constraints in mind. This is a very brief overview of the actual circuit for the neuron and for the synapse. Yeah, the red arrows depict individual gate voltages that control essential parameters of the neuron and synapse behavior, or we call them biases. And for instance, for the neuron, one gate voltage that controls the leak or defines the integration time constant of the neuron, another introduces the DC input, another controls the length of the refractory period, and so on. And so all of those biases are in fact controlling different parameters that you can set. So you can set the refractory period, you can provide DC pulses and observe the relaxation time constant. You can set excitatory inhibitory weights for synapse pulses and also the time constants for them. So this is what you expect the neuron, the chip to physically model. And it's important to note there's no such thing as starting and ending the simulation with this chip. It's rather physical emulation where the time is represented by itself. which means that the dynamics of the neurons are biologically plausible and are always running in real time. In fact, the emulation starts once you plug the chip in, which means that you need to really treat it as a biological system. You need to define the beginning and the end of the experiment yourself. And if I show you how this works in practice, this is practically what the live interface looks like. Here on the right, a lot of flickering dots are individual neurons, so they are colored only by the cores that they belong to. So here we have all 16 different cores from 4 different chips, and every time the pixel illuminates, it means that that neuron emitted a spike. And here on the left, we have 4 columns per each chip that control individual parameters that we can set for those cores. So remember that the parameters are shared between the cores. These are some default parameters that are set equal to all of the cores, but you see the variability of behavior between the different cores. So one of them are more active than others. And also within each core, you have some neurons that are almost always colored and others are not responsive at all. So this is the extent of variability. And then as a quick demonstration, let's look at the core 0 of chip 0, which would be this bottom core, bottom left one. If I go to the parameter that controls DC input, which is this slider, if we increase the DC input, we should see all of the neurons firing much more, and this is exactly what happens. So as I move the slider, all of those neurons begin to receive more input and fire much faster. I do not have if you actually do the measurement, you would see that it can go up to, the firing rates could go up to 300 hertz or so. If you go higher, then there's a good chance that there will be some problems with the router. So there's no chance that you would burn anything on the chip, but some of the cores can get stuck if there are too many events that the router has to process. Or for example, if I now increase the leakage to a very high value, none of the neurons would fire, and this is how you can silence them. It means that the leakage is so fast that none of the neurons are actually reaching their firing thresholds. This once again demonstrates the extent of variability between the cores. So on the left here, this is what happens if I just copy and paste the same parameters. Even though the width of individual distributions here, they are color-coded by the chip. So orange are 4 cores of chip 1, green are 4 cores of chip 3. What happens here is that even though they keep the width of 10 to 15%, as I introduced before, you can see that the means of those distributions are moved around quite a lot. So they can be variable as much as multiple sigmas. Why calibration is important, that it is in fact possible to change the biases such that the distribution of parameters is closer together, like this on the right. But to do that, you have to actually perform the calibration. During my PhD, what I have confirmed using the automated calibration procedures is that individual parameters distributed in different ways. So here are a few plots introducing different parameters such as excitatory weights, refractory periods, and membrane time constants of those neurons. And I found no correlation between those distributions. And I also found that they scale linearly, so the coefficient of variation stays the same. Also, the neurons that are typically faster, that have the faster time constant, regardless of the center of the distribution, they tend to stay in that part of the distribution. Or what I'm trying to show here is that you have generally predictable variability, and that leads to heterogeneity of behavior. So when you stimulate the neurons, you get a distribution of behaviors rather than them all behaving identically. And then when you measure some transfer functions, so you send in the input rate and you measure the output, the gray lines here show individual responses, and then if you average between those neurons, you get a much nicer, smoother average response, which leads us to one of the strategies how to work with the chip. You could use some clusters of neurons rather than individual ones, so that the responses of those clusters are more uniform between each other, and then you can get something like this three-dimensional diagram, where if you are operating in rate-based regime, you can see how the variability between those clusters changes with the cluster size. So the bigger the cluster, the lower the variability. Or the longer you wait, or the longer you integrate, you also have better precision or less variability between the cluster responses. Then you can find a sweet spot for your system. Maybe you want faster reaction time, and you can sacrifice some precision, and vice versa. This is the example of the network that I worked on specifically on DYNAP-SE1. These are so-called winner-take-all networks, where you have clusters of excitatory neurons recurrently connected within themselves and to their neighbors, and then the excitatory connections also go to the population of inhibitory neurons that globally inhibit back all of the excitatory clusters, which induces the competitive behavior between those clusters. And you can do a lot of interesting nonlinear operations between those clusters. So if you don't have any lateral connections, only one cluster is active at a time, you can tune those clusters like so that the network basically preserves the state. Only one cluster is active at a time in absence of inputs, and then when the input is presented, the activity can shift to another one. These structures are also called neural state machines. Or if you have some degree of these lateral connections, you can have soft winner-take-all when multiple clusters could be active at a time. And then you can encode inputs as with population codes, which you can see here on the right. So you can either do some filtering or restoration of signals. So you have some space-distributed, space-encoded signal where you encode a variable, one-dimensional variable from 0 to 1 using a so-called population bump. So the distribution of rates, and then you have essentially a ring attractor in this network where you have the activity bump moving around a network, or it can do a selective amplification of signals if you send multiple ambiguous signals. So this is exactly what you're observing here. Alternatively, if you would like to go away from rate coding and try and encode time using our integrator neurons, we could do it like so. If we take the same structure as the winner-take-all, but we only keep only one direction of the lateral excitatory connections, we can get a structure like this, still made out of clusters of individual neurons, except they sequentially activate each other. But because of all of the dynamics in synapses and neurons, there is a delay in propagation of the cluster activations. And like so, we get something called delay lines or synfire chains, where we can basically encode time delays in the input signals. If we have a single input on the left, and then it is active with some time pulses, these pulses would be fairly faithfully represented within the network. You can have multiple of those, and they can encode relative pulses in time. So you have special temporal sequences that can be still represented by a spiking network like this. And if you'd like to see how exactly it looks in practice, I can just show you this. So we have a couple of cores that I'll be showing, and then I have VS Code. I have already run some of the cells. I have a class that implements a winner-take-all network. I just instantiate a class, which is when the connections are actually applied to the chip. I can load the parameters that I saved in advance, and right away here we have now this population bump. So this green here is now the population of inhibitory neurons on core 1 of chip 1, and here is the population of excitatory neurons active. And I can also run a visualizer. Here is a little GUI that I wrote that can just interactively plot what's happening on the chip right now. It just retrieves the spikes with a few times a second. And this bottom left plot shows instantaneous firing rates of individual excitatory neurons. So we have 128 excitatory neurons. The dark blue shading is the input that I am sending them. So those are fixed rate Poisson input spike trains. The raster plot is at the top, so we have individual spikes plotted there, and then we have the inhibitory population that also fires back. So I can move the input from one location to the other, and we see how the activity shifts around. How the activity follows. Go to position 0.5. 0.8. So you can think about the entire axis as going from 0 to 1. So it's coding a one-dimensional variable from 0 to 1. But then if I set the amplitude of the bump to 0 of the input, our bump stays, but it starts drifting around. Sorry for the slightly low refresh rate. But you get the intuition that it's now drifting, specifically because of the noise and heterogeneity of individual neurons. You would ideally either make it follow the input or to represent the variable robustly, or you can have multiple populations connected to each other. Or I can demonstrate the input using a couple of bumps, and we can see the network attempting selective amplification. So the difference in firing rates of those two inputs is one is 100 Hertz and the other one is 70 Hertz. And the activity stays next to, with a stronger input. Now I can flip the rates around. I change that and the activity bump shifts to the other one. So there are some activations. The switch is not fully stable, but we see that the majority of the input stays around the stronger input. So this is the kind of behavior you can expect from the soft unity goals, for example. Or another demonstration of the time coding would be this one. So now I can just quickly reconfigure the chip to, so as I introduced before, I can show the behavior of some delay lines. It just takes seconds to reprogram the chip to change the connectivity within the core, and now we can have something like this, where I just declare the pulses, and then we can send our temporal signals. So a sequence of pulses across 3 different channels. I think the last sequence is just channel 1 with fixed delays. So yeah, you can see that the pulses are moving along those delay lines with fixed speeds, even though some of the spikes are happening earlier, some of them are happening a bit later. So the fronts of those traveling waves are not exactly straight. But this exactly shows the benefit of clustering neurons together, because on average, and because they are all interconnected within the clusters, it ensures that the propagation speed of those waves is actually constant. And this way you can quite robustly encode temporal signals. And my suggestion is to work with the chip using individual cells in Jupyter notebooks or just cells within Python scripts within VS Code, if you like. Because the part that takes the longest is the initialization of the chip. When you open the chip, it takes around a minute and a half to just clear all of the connections. But then the actual reprogramming of the matrix and updating the parameters is really, really fast, as I've demonstrated. To control DYNAP-SE1, we use Python. Specifically, we use the module called Samna, which is proprietary software from the company SceneSense, which manufactured the chips. This Samna module gives us this model object that we can interact with, and then there are 4 different pathways of what we can extract from the chip. And I will very slowly go around this diagram to just make sure it is quite clear what is possible. Once the chip is initialized, the first thing that we can do, we can stream the spikes out. So there's a system for filtering events that come from the chip. You can specify individual neurons that you're interested in, that you're listening to. And then it's implemented with the mechanism of buffered filters, which means that every time you call a function getEvents, it gives you the recorded data since the last call of this function. It runs in its own separate process, which means that you can just keep calling this function getEvents even a few times a second and just keep getting the data. Or you can run protocols of stimulation of individual neurons, and then only call it once afterwards to get the full recording over multiple seconds or minutes. You just need to be careful with not overflowing the memory. Then there's the API object that controls the analog connectors. So you can tell each core which membrane voltage to output. And then there's the configuration object that contains the biases that you set and the connection matrix. The model stores the state of the chip. You can read that state. You can do some changes. Then you can come up with a new configuration that you upload to the model, which is then in turn applied to the chip. And the final module is the onboard FPGA spike generators, which is the main and the only way to actually send any information to the chip, any spiking information. What you can do is you can either program it with a specific preloaded stimulus of, I believe it's 32,000 spikes long. So you can set some recording that would be uploaded to FPGA, and then you sort of hit play. And those events are streamed from special sources that we can call virtual neurons. Or alternatively, we can just set firing rates that would just be active continuously with the rate that you set. You should think about this as you have 4 chips of 1024 neurons each, but also you have this 5th virtual chip that plays a role of sources for virtual events that you preload. So to actually have some inputs on the chip, you need to preload those spike trains. You need to tell the router that you are actually creating those connections. And then you need to set the synapse parameters such that the neurons actually receive inputs. Overall, the sequence of working with the chip would look something like this. You have chip activity. And to interact with the chip, you have the onboard FPGA that you command to write the Poisson spike trains, and you would also ask it to give you the events that have been recorded. And you have your Python API, Python processing of how you would like to configure the chip. So at some point you would change the rates. It would take some time to reprogram those rates. It's on the level of tens of milliseconds, but it's non-negligible. And then the chip would do its thing. This change in inputs would affect the dynamics. Then you can change the stimulus again. You can reprogram the Poisson rates. It would propagate with after some delay and change the activity again. And then you can record back. So this function get events would keep the entire history of what happened with the chip over here in this region in time. And the recording would continue within the buffered filter until we call the get events again. And the second call would only retrieve the history of activity of the chip in here. So this is the general framework. You can either have it like this, where you specify yourself some moments in time when you send inputs and when you change things. Or if you are training something in a more traditional machine learning philosophy where you have frames, then it would look something like this, where you preload something, you let it play, you record the chip activity, you record the response, you process that, then you make some decisions on changing the parameters, then you preload the new sequence, the new frame, then it plays again, and so on. Then you have some sort of downtime of the chip where you don't really use the response, but the chip doesn't stop. This is the point I'm trying to convey. This is that it's the constantly active dynamical system on the chip that never stops, unlike the digital accelerators. What I've been covering so far were always the static networks, right? So that we always just set the fixed connectivity matrix. We set some parameters, or we change parameters, but the network itself stays the same. Well, it doesn't have to stay the same. You are able to reprogram the matrix on the fly. So while the chip is running, while you have the emulation of dynamics, you can reprogram individual connections between neurons on the fly, which means that you can come up with some cheap in the loop protocols, which would look something like this. This is the rough diagram of a system that I also tried implementing, is that you can have your neurons, synapses over here, you get some events, then on PC, you get those events, you sort them, and then you can apply some arbitrary learning rule, some update rule for your network that you design yourself. It could be either Hebbian or some form of gradient descent or whatever you can come up with. And then that would change some ideal version of the matrix that you have. And then you need to quantize it because the connections between the neurons are binary, or there are some tricks to have some slightly better precision, but it's still like on the level of 2, maximum 3 bits between each pair of neurons. So it's really low resolution connectivity between the neurons, but it's flexible, so you can modify those connections on the fly. And you would ideally, my suggestion to do it like this is to keep the precise network at all times, and then each time you would like to update the matrices to do the quantization step when you apply it back to the chip. And then that in turn impacts the dynamics of neurons and synapses because the matrix is different, and so on. So you can have a logic loop like this that lets you train networks on DYNAP-SE chips. And then a trick that has been proven to be quite useful is to use stochastic rounding. So when you do this quantization step, or the transition from precise network to quantized, you can, instead of deterministically rounding up or down to the next integer value, you can rather use those fractional parts as probabilities of rounding up or down, and apply to gradient descent, for example. Then the network converges much better to some better global optimum compared to deterministic one, where it would start oscillating between a couple of states. So if you would like to work with one of the DYNAP-SE1 boards, there are 3 ways you can do it. Most of them are connected to this server called Zemo that is physically located at INI. You can access that server using the SSH through the UZH VPN, and you can run code on your machine and send configuration commands and retrieve spikes, do changes like that. But in that case, you do not have the access to interactive GUI. There is also currently a digital oscilloscope board available directly at the server, so you can get analog traces when accessing Zemo remotely. Option number 2 is to just come to INI directly, and you can do some of the experiments or some calibration locally when you just sit down next to the machine and get access to all of the interactive features to quickly tune something for your network. And the scenario for this is such that you do the calibration, save the parameters, and then keep working remotely. And the last option is if you're either not part of the INI framework, or if you're somehow have the access to the board remotely, then it's a local scenario when you have your own board, you're just connecting to your own PC. The intended operating system in all scenarios is, of course, Linux, but it's also been confirmed that with Mac or using the WSL on Windows, it is also possible to run the DYNAP-SE1 software. There are some tricks to configuring those that I will not go into details today. Overall, this concludes the DYNAP-SE1 chip overview. The main intuition about the chip is that it is always on. You never start or stop the experiment. It really needs to be treated as a biological system where you design when the experiment starts and when it ends. There's no such thing as just fixed initial condition. If you record from multiple neurons, you can only record spikes, but also subthreshold voltages, or the membrane voltage dynamics could also be captured, but only from one neuron at a time, and you need an oscilloscope to monitor them. Heterogeneity is everywhere, so you always have some distribution of behaviors from the neurons, and the main annoying constraint with the chip is so that you can only set the mean value of the distribution of each parameter, and the parameters that you set are just some arbitrary values that set the bits for bias generators, so it's not in any meaningful numerical values, but this is something you learn to live with. You can have reconfigurable connectivity between all of the neurons, but you have quite low precision of individual weights. The good thing, you can change them on the fly while the chip is active. the inputs that you send should be either preloaded FPGA spike trains, or you program the onboard Poisson spike generators to provide spike trains with fixed connectivity. And then, yeah, the live updates could be used for some sort of learning algorithms. And if you go to code.ini.uzh.ch, you have this DYNAP-SE1 repository that you need to clone to work with DYNAP-SE1 once you have the access. And in this repository, we are trying to provide comprehensive links to everything concerning the chip at one place. We also have the booking system so that the usage of the chips is not clashing, because they are currently in limited supply. If too many people are trying to use them, they need to share. And then, yes, you have all of the documentation here. You have the installation guides, and then you have examples that walk you through creation of allocating the neurons, creating the connections between them, providing inputs. So if you have a project that you would like to implement on DYNAP-SE, this is the place to start. And then, of course, as one of the main developers for this software, don't hesitate to write me an email asking specific questions. I'll be always happy to help. I might not answer right away, but I will also always do my best to give as full of the explanation as I can. But with this, I would finish this video here. And with this, I would conclude this video. I hope I gave enough of the overview to give the impression of what the chip is and capable of. And if you have any questions, don't hesitate and ask me using the email. Bye-bye.